Hello guys, this is DrJan knows chemistry and welcome to my YouTube channel. Alright, in today's video we're going to be discussing alkanes, alright, and this is part 2 actually. I hope you have watched part 1 where I introduced alkanes and I introduced them as the most important organic compound. Yes, the most important organic compound because every other organic compound depends on them. Alright, they have their root here. Okay, be it alkanes, alkynes, alkanos, alkana, alkanones, alkanoic acid. I'm not speaking in tongues. Those are the other class of organic compounds that depend solely on this. Now imagine if you have issues with alkanes. You're going to have issues with those chains of organic compounds that I just mentioned, and definitely you will say organic chemistry is tough. All right, so if you're a student just like any of you and you have issues you find difficult, organic chemistry is like your difficult topic, all right, just sit down, calm down, take your pen and jot as much as you can and work with me. All right, at the end of this video you're going to sort everything out, provided you have watched the first part, which is part 1 to alkanes. So without wasting time, let's quickly do this and let's get into today's business. All right, just like I said, alkanes are very, very important. Every other organic compound is built from it, all right? Alkenes, alkynes, alkanos, alkana, alkanones, alkanoic acid. There are so many esters, all sort of other compounds. They're built from it, all right? And the reason why majority of science students, all right, you could be part of it, and that's possibly the reason why you're watching this video. You find this difficult because of the fact that alkanes are not well understood, because once it is well understood, the other class of organic compound just work on them like this, like a boss. All right, so let's quickly jump into it. In my last video, part 1 of alkanes, I discussed the nomenclature, all right, and I think I want to continue from it now before we get to the main part of today's video. All right, I will just give you another compound to name and I will name it for you. Once I drop the structure, make sure you pause the video, try it and see if you can name it correctly. All right, let's example 1 now. Give the IUPAC nomenclature of this compound. All right, look at that. All right. All right, you can pause the video and look at it. What is the IUPAC nomenclature of this particular compound? All right, it has 2 carbon atoms. All right, then all these halogen substrate in it. All right, so let's quickly pause the video and solve it and let's see now. All right, so when you look at this, like I've said, you can name it 1, 2, all right, or another person can name this 1, 2. So that means I'm going to provide the 2 names. One will be written in red, that means we are moving from this side. Another one will be written in black, so we move this way. All right, this is just to reinforce our already established rule that where do we move from actually. But because we're starting from part 2, let's name it this way. All right, we've already established that you move from the position. If you want to do the numbering, you start from the position that gives you the lower number to the position of the substituent. All right, you may be asking, what are substituents? Go and watch part 1. All right, let's go about that. All right, you should know that these are substituents now. All right, because they have replaced the hydrogen there. All right, let's move from here. That is 1, 2. Now Br there is bromo. All right, F is fluoro. All right, B is bromo. All right, and C is chloro. All right, so this is C, this is B, and this is F. Whenever we have different substituents, all right, we name them in alphabetical order. That shows that we're naming bromo first. All right, so bromo is attached to carbon number 1, that is there. All right, so we say 1 bromo. All right, then after bromo we are naming chloro. That is still 1 chloro. Remember, I'm naming from black here. All right, 1 bromo. All right, then we have this one is attached to position 2, this one also position 2, this one also position 2. Remember, this is, we are using this 1, 2 to name. Then the red one, I will name it over there. Okay, So how many fluoro group? That is trifluoro. Then what is the longest chain? It's just ethane. All right, that is, we name it from this side. All right, let's name it from this side. Remember now, we now have red 1 and 2, so that you won't get confused. Let me put it this way now. All right, so here we are still going to name bromo first, because that's the first. When we're talking about alphabetical order, we have B there, we have C here, just like similar. So but now it's 2 bromo. Can you see that? Then chloro is attached to carbon number 2. That is still 2 chloro. All right. Then this is 1, the first one. The second one is still 1. The third one is still 1. Position 1, trifluoro. Then the longest chain is still ethane, which is 2 carbon atoms. All right. So when you see, if this one were to be your JAMB questions or a WAEC question, this would be option A, this would be option B. All right, somebody will name it this way. So I got the answer. Wow. All right, another person will say, I got it. Everybody has the answer, but there can only be one correct answer, right? So if you see something like this, where do we name from? We just said that which particular position here, which numbering gives you the lower number to position of substituents. You can see that this is position 1, 1, 2, 2, 2. If you add all those numbers together, you get 1 plus 1 plus 2 plus 2 plus 2. All right, plus 2 in 3 places, that is 8. All right, if you do this one, 2 plus 2, 1 plus 1, you get 7. Okay, 2 plus 2 plus 1 plus 1 plus 1, you get 7. But the point I'm trying to make is just that you see that this place has a lower number to the position of substituent. All right, the position of substituent 1, 1, 1 has actually kicked this off. This is 1, 1, 2, but this is 2, 2. But by the time you add the numbers together, you find out that this has a lower number. So that is why this is the correct naming, not this one. But if you are writing exam, you're likely going to see the options. So this is a very popular compound. You can find out yourself. And in industry or in hospital, we call it halothane. All right, halothane. It's just like ethane, 2 carbon system. Halo, subset halogens. This is halogen, this halogen is halogen. All right, it's an anesthetic agent. All right, if you want to operate on a patient, you have to knock them out, let them sleep, so you can operate them very well, and they wake up again, they find out that the operation has been done. All right, so imagine the doctor telling nurse and saying, please get me 2 bromo, 2 chloro, 1 trifluoroethane to a patient. All right, that's too long. If that patient has just some few seconds to leave before attention, so of course we lost that patient because of the fact that the name is too long. We don't have to tell nurse, give me 2 bromo, 2 chloro, 1 trifluoroethane, instead of just give me other thing. All right, so that is why we have brand name. Some of the stuff we call paracetamol is actually like para-amino acetaminophenol. All right, so imagine you want to buy paracetamol, you go to the chemist shop and say, I want to buy para-amino acetaminophenol. They will say they don't have, possibly. All right, so that is paracetamol. We have trade name, all right, common name, trivial name, and the IUPAC name. All right, so this is halothane. All right, and I have told you this is how we get to name it. All right, so let's see example 2. All right, so let's take it example 2. We have another compound. Let's say I just give you this randomly. All right, I put C2H5 here, and I put C3H7 here. All right, so I hope you've seen that. This is CH3, and this is Cl. This is Br. This is Cl again. Okay, I hope you're seeing that. Now we have H. All right. So if you have to name this, let me make this one straight to me. So C3H7. I hope you have seen that. We have this way. All right. I want to put to be able to test you to do something. All right, I want you to see something. All right, so this is lovely now. This is lovely. All right, look at this compound. Pause the video and let's name it together. some of you may be wondering, like, oh, how do we name this? The first thing you need to do is to get the longest continuous chain. Remember, it's not just longest chain, longest continuous chain. This one looks like longest, all right, but it may not be. So let's quickly try it together now, all right. This one is carbon 1, 2, 3, 4, 5. That is 5 carbon atoms. Okay, let's see whether we can have another one. These are 2 carbon atoms, okay. If it is C2H5, we can as well write it like this. This is C2H5, okay, before it links to the C there. All right, so this is 1, 2, like 1, 2, 3, 4, 5, 6. That's longer than 5. Can you see? So we've seen C5, we've seen 6, 6, right? Let's see whether we can see more than that. 1, 2, 3, 4, 5, 6, 7. You are seeing 6, 7. All right, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, so 7 is actually the longest, which is like this. Can you see that? That is the longest continuous chain. So I want to transform this particular compound now, so that you will see that, oh, it is actually easy. Look at it. This is C2. Look at this. 1, 2. Single bond can be rotated. All right, you can just, it's just like a rubber that can just straighten, or something you can just straighten like this. So that is just what it is. So this is now my longest chain. So it's continuous because you, no matter how, even if it bends, you go with it. As long as you're climbing on carbon, you have not got to the dead end. Okay, look at this. I can climb on this carbon like that, and here I can't jump anywhere. If I jump, this is big water, so that's the end. So that's why I see 5. Then I got this 6 from where? 1, 2, 3, 4. Okay, 1, 2, 3, 4, 5, 6. Okay, so I got this 7 from 1, 2, 3, 4, 5, 6, 7. Okay, so I keep going. So this is the first carbon. Look at it. This is the second carbon too. So the H5 around it is this. I want to transform the compound so that you can see that that is small to alkane, and that's the reason why people find alkynes, and other classes of organic compounds very difficult. All right, we have C2H5. That is it. This C here is this third one. All right, and this C is carrying what? Cl. Can you see? Then when you look at this place, that is CH3, which I can combine like this. Look at this. C2H5, that is it. I just straighten it. I want to straighten this one so that, look at this, I brought this one here. So C2H5, that is it. This is Cl. This same C is attached to CH3. Can you see? So this same C attached to next C. This next C is carrying Br. Can you see? So this guy is now also this particular C that is carrying Br is attached to the carbon carrying 3 carbon. 1, 2, 3. Can you see? So then this same C is attached to C2H5. So I can put C2H5 here. If you look at this very well, and if you can see it, you find out that it's actually the same thing. All right, so the rest are H. C3, this is C3H7. 1, 2, 3. H2, 3, 4, 5, 6, 7. Can you see that? So this is beautiful. So most of you find this difficult, this transformation, and if you cannot transform this in your head, then it becomes very difficult. It's just like you can as well name it the way it is. This is the longest chain now. All right, so that is 1, 2, 3, 4, 5, 6, 7. That is heptane. All right, the name of an alkane with 7 carbon atoms is heptane. All right, so you can see 1, 2, 3. From 3 I got to the methyl group, and 4 I got this guy. So 3 has this substituent, and 4 has this guy. If I come from here, 1, 2, 3, get to 4 first. 5. So we can as well now name it. How do we go about it? If I name from here 1, 2, 3, 4, I'll get to 4. My substituent will be at position 4 and 5. But if I come here 1, 2, 3, 4, my substituent will be at position 3 and 4. So that is why it's to name from here. All right, are you getting it now? If I have naming from here 1, 2, 3, 4, 5, 6, 7, can you see that my naming continues to 7, that is the longest continuous chain, heptane. But the substituent are attached to carbon number 3 and carbon number 4. But if I name it, let me use red pen from this one. If I name it from this end, all right, from this end, this is 1, this is 2, this is 3, this is 4, this is 5, this is 6, this is 7. All right, my substituent will be of position 4 and 5. But from here, position 3 and 4. So that's why this is the right naming. But also remember that we have substituents of different kinds here. In fact, all the substituents are different. Chlorine, which is named as, will be named as chloro. Bromine will be named as bromo. CH3 is methyl. What about C2H5? That is ethyl. All right. In the first video, I told you how to name these alkyl substituents. All right. So let's get into the business. We are naming bromo first, and we are coming from here 1, 2, 3, 4. So that is 4 bromo. Can you see that? Alpha bromo remains C. So 3 chloro. I said between numbers and letter, you put dash. That hyphen was there. Between two numbers, you put comma. But of course, we are having just one of them here. All right. So after that, we have ethyl. D, C, D, E. Ethyl. This is ethyl. So 4 ethyl. Can you see that? Then, what is that? 3 methyl. Dash methyl. That's the name. Heptane. 4 bromo, 3 chloro, 4 ethyl, 3 methyl heptane. That is the name for this compound. I can see that it's not really difficult. But how would you be able to know how to get the longest chain? That's the first one. So, and I'm teaching you already. Getting the longest chain, you must keep working on each carbon. This is one. If you want to name it from here, let me just tell you from here without straightening, it's still okay. After you have identified this as your longest chain, this is 1, 2, 3, 4, 5, 6, 7. All right. So 1, 2, 3. At position 3, you have chloro and methyl. Look at this chloro and methyl. At position 4, you have this guy. Because this is chain, so this whole thing becomes the substituent. That's why sometimes I love mapping the longest chain out, and I want you to do the same thing. It gives you the clear picture of what is substituent, because once you've mapped it out, then every other thing becomes substituent. Look at this guy. So every other thing becomes substituent. Anything that has replaced hydrogen, all right, becomes the substituent. Let's look at another example 3, whether you can actually try that again. Okay, so let me give you another one, and this time maybe I'll make it a bit difficult, or let me just leave it. Okay, let's say we have C, CH3, C2H5. All right, Cl, C2H5, and C3H7. All right. Okay, so look at this. Does it look the same way? I think so. All right, maybe we should just leave. Okay, let's treat it. Let's treat it still the same way. All right. So look at this. The longest chain. Some of you may not know. The longest chain is this, like if you have this one, look at this, 1, 2, because that is just 2, or 1, 2, 3, or 1, 2, 3, 4, 5. Are you seeing what I'm saying? 1, 2, 3. We keep moving, line. Okay, it ends there. This is 1, 2, 3, 4, 5. All right. This is 1, 2, 3, 4. Can you see that? 1, 2, 3, 4, 5. This is 1, 2, 3, 4, 5, 6, 7. Can you see that? This is also 1, 2, 3, 4, 5, 6, 7. So 7 is actually the one. Whether you move like this, that is 7, or you move like this, you're going to get the same thing. All right, no matter how you move this thing. So of course, what is important is that we have to locate the position of the longest chain first, and I've identified it to be 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Just like this one. All right, or 1, 2, 3, 4, 5, 6, 7. All right, 6, 7. So let's map out this guy. Just like we did. All right, if you map that one out, that shows that these are methyl group, these are ethyl group, that those ones are substituents. All right, so this guy, this is the longest chain, which is 7. All right, once you have that, that is the heptane again. Why is it heptane? 1, 2, 3, 4, 5, 6, 7. All right, some of you will say, oh, I understood, I came when they taught me, because they didn't teach you this part, and this is the most difficult part. All right, they just gave you this one you say straight chain. You thought you understood. You didn't understand anything. Once you don't understand this part, then you don't know alkane at all. So it's better for you to know how to work with the longest continuous chain when you have different ways you can move. All right, so if I do like this, 1, 2, 3, 4, 5, 6, 7, I'll still get the same thing. All right, you can try it so you can see that it's true. So but I move 1, 2, 3, 4, 5, 6, 7. That's my longest chain. All right, if this is my 2 carbon, this is the third one. So I have chloro, I have methyl, I have ethyl. So this is ethyl. Oh, sorry, but this is ethyl. All right, ethyl group. All right, this is methyl group. This is chloro. So we are naming C first before ethyl and before methyl. Methyl is going to be the last, but heptane, because it has the longest chain. Remember, this is C2. The third one has chloro. The fourth one. So I can now rename it, even as it bends like that. Let me do it for you. 1, 2. That is C2. The third carbon is this guy. All right. So let me put the methyl group in red. Okay, this guy. Okay. So this next one is this C. All right. So followed by this C. All right. We now have another C3 there. C3H7. 1, 2, 3. 1, 5, 6, 7. Can you see that? So you have to understand how to name this thing before you name. Most of you don't know how to do this, and that's why you think you know, you understand naming of organic compounds without knowing anything. All right, CH3, then C2H5, then we have CL here again. So this is the same compound. I can as well straighten it, so this one will just be long, and that's what we have there. All right, so this is my first carbon, second, third, 4, 5, 6, 7. That makes me to name it as heptane. All right, if you look at this, if I move this way, I will get to this substrate quicker or faster. All right, look at this. 1, 2, 3, 4. Position 3 and position 4, that's where I have my substrate. But here, 1, 2, 3, 4, 5, position 4 and 5. All right, so it looks like the first one we named, and I really love that. All right, so let's quickly name this heptane. All right, so the next thing we are naming is chlorine, because it starts from C. Whenever we have substituents of different kinds, we name them in alphabetical order. All right, so let's see that now. Okay, so chlorine is at position 3 and 4. So you say 3, 4. How many chlorine atoms die? There are 2. So that's why I put 2 here of the same kind. Okay, 2 dichloro. All right. So after that, we are naming ethyl. Ethyl is at position number 3. 3 ethyl. Okay. So after that, what is that? 4 methyl. Can you see? 4 methyl. Then heptane. So until you know how to work out your way to the longest continuous chain, especially when you have multiple routes that you can follow, then I can say, wow, you now understood how to name alkanes. Most of you are used to just straight chain, all right? And then you say, oh, I know how to name all this one. So we started from that, from the part 1. So these are just the difficult aspect where you have to learn how to do that, all right? So sometimes they can tell you to name this CH3, CH3, CHCl, CH2, 2, all right, then CH3. All right, so this is, you can say you should name this IUPAC nomenclature. You'll be wondering, like, what is this? All right, all you need to do when you have something like this, you can pause the video, try it, then I will actually bring it up again and then we'll work it together. All right, let's go now. Okay, all you need to do, you can transform it. CH3, just they clip the wings for you, so flap the wing again. CH, I can put H or H up. CH3, can you see? CH, CH3, then CHCl, CH again, Cl, can you see? Then CH2 in 2 places, CH2, CH2. Is that simple? All right. Then CH3. This is the compound. This is the compound. It's the same thing. CH3, CH3, CHCl, CH2 in 2 places, then CH3. That's all. So longest chain. Of course, these are the substituents. Can you see that? So this is so straightforward. But the only thing I wanted to test is when they give you the structure in this way, you'll be able to name it, and that's what we are testing now, right? So 1, 2, 3, 4, 5, 6. Have you seen that? So that is hexane. The name of an alkane with 6 carbon atoms is hexane. All right, but we have chloro and methyl substituent. Chloro is what we're naming first, because C comes before methyl. So some of you say, how do you know that this is methyl? Go and watch the first part, which is alkane part 1. All right, so chloro is at position 3, so you say 3 chloro. All right, then what? 2 methyl hexane. All right, so that's just the name, but look at the way they give it. All right, it can be very confusing, but just don't bother. Stretch the wings and you'll be able to get it. Remember, in writing the structure of organic compounds, carbon is tetravalent, okay? So 4 bonds must be around it. Don't be generous and don't be stingy. For some substance to stay as a compound, alkanes, all right? Or let's just say organic compound, any organic compound, the carbon around must be tetravalent, okay? That means 4 bonds must be around it. So don't joke with that. Okay, so let's just run it off when it comes to naming, because I can continue to give you compounds to name and all that. All you need to do is just, if you have any compound that you named and you find it very difficult, just put it in the comment section. We'll name it together and make the video for you. All right. So that's I can tell you I will do that for you. All right. So I think we want to wrap up the naming now, nomenclature, because from there I hope you can do that. All right. So let me just give you another group. Apart from alkanes, we have cycloalkanes. That is just like we're not spending time on cycloalkanes. All right, cycloalkanes just means that alkanes in cyclic form. All right, let me give you an example now. Let's say we have this guy. All right, because the 3 bonds, look at this, remain 2 bonds. This one remain 2 bonds. This one remain 2 bonds. All right, so we have this one, alkane, because it's single bonded. Can you see what do you have there? This is propane because of C3 propane. It's very simple, propane, but because it's cyclic, like a ring is round, so we just call it cyclopropane. Remember, it has only C3 H what? H6. You can see that it does not conform to CnH2n plus 2. All right, so it's not the general formula is not this. In fact, the general formula is that every carbon has 2 hydrogens, so it's CnH2n. It looks like that of alkanes, okay, but they are cyclopropane. They are cycloalkanes because they are alkanes in a cyclic form. Let me tell you another one. Let me give you this. Can you see what would this be? So this will be 2, 2. All right, 2 carbon atoms. 2 hydrogen atoms will be with each carbon atom. Can you see that? This is butane because of 4 carbon atoms. So butane. But because it's cyclic, call it cyclobutane. The one word, okay, cyclopropane, cyclobutane. I hope that is clear. All right. So if you want to draw now, draw cyclopentane, cyclohexane, and tell me the formula there. All right. So that is how it is. So let me quickly give you number 3 now. That's cyclopropane, cyclopentane. All right. 1, 2, 3, 4, 5. Okay. So that is it. Because it's cyclic, So we'll do it by 2 hydrogen atoms to make it 4 bonds around carbon. I see. So this guy becomes cyclopentane. It's that simple. Alright. This is pentane because it has 5 carbon atoms, then cyclopentane. Alright. So that is very simple. Okay, don't tell me that it's difficult, but sometimes we can just write it skeletal like this. So this like this. This is cyclobutane. This is propane. This is cyclopentane. This is cyclohexane. Cyclohexane is 6,6H12 because this is 1C, making 6s. Then each of them will have 2. Alright. So it's like when you reduce benzene by adding hydrogen, it's able to saturate all the pi bonds there. Then you have cyclohexane. Alright, I hope that is clear. So just to have that one to group, because sometimes we want to need this for something. Alright, we're not going to their chemistry really, but just to tell you that the other class of organic compounds are there. Alright, so we are moving straight into isomerism. That is isomerism in alkanes. Alright, what is isomerism? Isomerism is the existence of 2 or more compounds with the same molecular formula but different structures. Alright, that means we can have the same molecular formula, but because carbon has a funny way of making straight chain and it can join from the other end and make branch chain, it can even want to go cyclic. Alright, so it may not make us to like now see that the same molecular formula cannot have different structures. That phenomenon is what we call isomerism. So isomerism is the existence of 2 or more compounds with the same molecular formula but different structures. So when you have a molecular formula, how many structures, different compounds can you name from it? And that's what we mean by isomerisms. And each of them will be called an isomer. Alright, so isomerism is the existence of 2 or more compounds with the same molecular formula but different structures. So let's work out this one now. For example, let's say we have C4H10. Alright, C4H10 is a molecular formula. Don't forget the difference between a molecular formula and a proof formula. A molecular formula is a formula that shows the actual number of atoms present in one molecule of the compound. Actual number of what? Atoms. Alright, and a proof formula is one that shows the simplest whole number ratio. Alright, let me tell you something. This is like C4H10. This is the molecular formula. If I cut it this way, the simplest whole number ratio is C2H5. This is not the actual number of atoms or elements that are present in the molecule of the particular compound. It's just C2H5 that is the simplest whole number ratio. Alright, let me use benzene as an example because I want to tamper with this now. Alright, benzene is 6H6. That is the molecular formula of benzene because it actually contains 6 carbon atoms and 6 hydrogen atoms in one molecule of benzene. Alright, but what is the empirical formula? The simplest whole number ratio. So you can say 2 goes there, but 6 goes there. So CH is the empirical formula of benzene, while 6H6 is the molecular formula. This shows the actual number. So by saying this is the formula of benzene, so this is the molecular formula. But empirical formula shows, so 2 different compounds can have the same empirical formula, but they don't have the same molecular formula. For example, if you look at ethane, ethane is C2H2. Ethane actually contains C2H2. Look at the structure. C2H2, that's triple bond. Benzene, 6 is H6. Alright, and this is benzene. I've told you before, I think in the first video of alkanes, I did it to double bond like that, revolving. Alright, so that is 6 is H6. Can you see? There are 2 different compounds. Let's say ethane and okay, this is aromatic hydrocarbon. Both of them are hydrocarbons. Why? Because they contain only carbon and hydrogen only. They don't have any other element. But this aromatic hydrocarbon, which is This is one of the unsaturated hydrocarbons, all right, alkanes. All right, now look at this. What is the empirical formula of this guy? Empirical formula is the simplest whole number ratio. So this one will be CH. Empirical formula of this one is also CH. So two different compounds can have the same empirical formula. So that shows that the empirical formula is not the main thing, all right? So the molecular formula, the empirical formula. The empirical formula just shows the simplest whole number ratio of the atoms present in one molecule of the compound. All right, so when you have a molecular formula, how many different compounds can we draw from it? How many different structures? So some of you just say this is butane. Well, it may not be butane. A molecular formula shows the actual number of atoms present in one molecule of the compound. So this is a particular hydrocarbon. That hydrocarbon has 4 carbon atoms and 10 hydrogen. All right, so if we want to draw up the isomers present there, you know, we say isomers have the same molecular formula but different structure. The first one can now be butane. If it is this guy, so if it is this guy, it's now butane. Can you see that? If it's this guy, then it is butane. All right, so this is butane now. All right, because we have C4H10. So this is our butane. Is it possible for us to have another compound that will have C4H10, but it is not butane? The answer is yes. Look at this, 1, 2, 3, 4. That is for butane. You now clean this last one, all right? So we make it C3. So if I place that C here, are you saying something, please? So if I continue this one, H, look at that. You have to pay attention here very well. Please pay attention. Can you see? This compound, it looks different from this, but it's not different actually, because I told you that in single bond we can rotate it. So it's still, despite the fact that it's not straight, it is still butane. All right. So that C, if I now decide to place it at the middle, can you see where I place it? It can be up here, it can be down there. All right. If I place it there, and if I switch it, if it can't be 4 again, 1, 2, 3, 1, 2, 3, 1. So there is no 4 longest chain again. So that shows that this is a different compound from this. All right, most students have a lot of issues. The first one I drew, I put the C here. They will say it's another isomer, because once you count it, it's going to have C4H10. All right, look at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That is H, C4. So if I place this H3 here, it's still going to have, but it looks different. No. Once you have this, the first one looks like this. Remember, 1, 2, 3, 4. The second one now looks like this. 1, 2, 3, okay, 4. So what you need to do is just straighten it. Single bond can be rotated. It's still the same thing, all right? Just like you have iron that is bending, so just straighten it, and then the same compound. So, but this is, there's no way you can, except to pull this one, you now join it here. You can't shift it and then it becomes the same thing like this. So this is different from this. Of course, since we are done with naming, we can as well quickly do what? We can do this, all right? So this is longest chain is 3, so that is propane. Now this is methyl group, it's attached to carbon number 2. All right, so this is 2-methyl. All right, 2-methylpropane and butane, they are both isomers of this guy. All right, I hope you have seen that. They are both what? Isomers of this guy. So that's the reason why we call them isomers. They have the same molecular formula. If you count it, this is C4H10, this is also C4H10, but they have different names. Can you see? Different structures, which gives us different names. So that's what we mean by isomerism. Existence of 2 or more compounds with the same molecular formula but different structures, and that gives us the isomers. Let's look at another molecular formula, and then you will start working out how many. Okay, how many what? stuff we have there. So let's work out that, write the structures, give the name and structure, give the IUPAC, that is IUPAC name and structure for each of the possible isomers with the molecular formula C5H12. Let's look at that. C5H12. We have to give the IUPAC name and the structure for each of the possible isomer with the molecular formula C5H12. So that's what we're working with, C5H12 now. So let's see. The first one, because it's C5H12, just let's start from C5. All right, let's see if we put all the H, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This one is the normal pentane. Sometimes you see this N. It's just a straight chain, unbranched stuff. So that is normal pentane. If you count it, C is 5 and H is 12. So can we work out another one that is different from this? So I say you cut off one carbon and you place it at the end. You place it at this end, no matter how it looks bent, it still can be straightened because it's double bond. Single bond can be easily rotated. All right, so we have this guy here, 1, 2, 3, 4 now. So if I place C here, I can rotate it. Is this one. If I place the C here, that is what majority of you don't know, and that's why this gives you a lot of problems. Some of you, so I remember I said, hi, somebody taught me, I know how to name Alkanes, sir, test me. Yeah, I already know, I just gave him this kind of conference. Then he missed it. The person that taught him, he went to meet and the person missed it too. All right, so you now see that it's not just Alkanes. Actually, this is where the difficulty is. It's not just straight chain like this that you can easily name. All right, most of you don't know these issues of when you put at the other end, instead of them, they will name it as 1-methyl butane. All right, but it's at the other end, so I can keep climbing 1, 2, 3, 4. I'll still jump because there is a bridge that I can continue to link. If you like, let it move like this. I will still continue to move. You see long chain, so I'll move like this, move with it, except if you disconnect it and place it here. So if I go like this, I can go like this, I move like that. So the first thing you need to do after you have done the main one, which is the straight chain, you now want to have the branch. Don't place it, don't be tempted to place it at the end. Place it at the end, it just elongates the chain. Instead of you thinking it's 4, it's still 5 because you keep moving. So let's place it here. Let me place it here first so that you can see. The second one, I want to place it. Remember, I place it here. I've told you not to place it here because it's just the same thing that you're repeating. Most of them don't know they are repeating this one when they do that. All right, I'm just showing you, and that's why this is very, very important. Don't joke. Look at it very well. I placed my C here for a reason. You can see I wanted to place it here. I decided to place it here again. All right. We want to see whether this and this, they are the same or different compounds. Okay, so let's look at that. So let me pick H. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Can you see? It will just click. As long as you make the carbon tetravalent, like you put the 4 bonds around it, the number of hydrogen will just click. So don't disturb yourself. I don't disturb myself planting hydrogen. Once I do it, it clicks. All right. So what is this longest chain here? 1, 2, 3, 4. 1, 2, 3, 4. Well, you can't see 5 because we started from 5 and I cut it. So it's the 4 that is there. And I tried to make it straight like this. So that's the 4. So this is a methyl substituent that displaces hydrogen. So what is the name of an alkane with 4 carbon atoms? That is butane. Don't forget that. Okay, so methyl group is attached to carbon number 2. 1, 2, 3, 4. So that is 2-methyl butane. All right, let's try to name this so that we'll see whether it's another compound entirely. All right, we put H, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 again. So you can see. Now remember, I told you that when you are naming alkane, first of all, you get the longest continuous chain. All right, so the longest continuous chain is still 4, just like this one. But now, where are we naming from? I decided to name from here because if I name from here, it will give me 3 to this position of substituent, and I know that I will get to this substituent quicker here. So you take the route that is closer to the position of the substituent. Just like you're traveling somewhere and you must trek, you trek for 3 days or 2 days. You choose 2 days. All right, trekking for 3 days could get you weakened or kill you. So you have to choose the one that is very convenient. So the naming is not going to be from here. It's going to be from here. 1, 2, 3, 4. So butane for 4, then it's still going to be 2-methyl. So which is the same thing. So this compound is the same thing. It's just like this thing. You flip it and form this. Look at this where methyl is. That is this cover of this stuff. So once you flip it, it forms this. So it's the same thing, just like your pen standing like this and like this. So this compound and this compound, they are not extra isomer. Remember, this one has C5H12, this one has C5H12. So that shows that N-pentane and 2-methylbutane, they are isomer of C5H12. Now, can we draw another compound? Okay, we have another compound that is, apart from those two, are they the only isomers that we can derive from C5H12? The next thing we want to do is to reduce it to what? To 3 carbon atoms. Remember, we started from 5, then 4, then we are going to 3. 1, 2, 3. All right, we have 2 carbon atoms left. If you put one here and one here, do you know it's still the same compound? Because once I do like this, then it's straightened up like this. All right. Do you know if you do like this, it's still the same compound once I do like this? So this is where the real issue is, and most students are like, Jesus. So this is the secret. All right, they keep messing up themselves by giving the name that does not exist because they don't know that single bond can be rotated, and at the same time they don't really know how do you say this compound and this compound are the same. And I hope you're seeing the secret now, so don't joke with it. All right, let's go on. So what do you do if you have this? So maybe there is no more isomer. So, but let's see. If I put C here and C here, can you see? It looks different. So this structure looks straight. This one looks like this. Can you see? It's not, you can't straighten it and form this. And this one looks like cross. So can you see that? They are different. All of them have C5. So if they have one bond around C. So if I put 3 bonds here, that is 12 for hydrogen. Make it 4. So look at this compound now. This is another compound that is different from all the 2 that we have drawn and named up there. All right. So let's try to see how do we name this compound now. All right. If you look at it, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. It's just 3. When it's like that, pick this. Once you have picked that, this becomes substituents. These 2, they are now substituents. I hope you're seeing that. So those 2, they are substituent. Then because it's 2, what is it called? Propane. Okay, so propane is there. All right. Because it's because we have methyl group at position 2, this one and this one. So we have one at position 2, this one. We have the second one at position 2. How many methyl? Methyl. So this is 2,2-dimethylpropane, and you still have C5H12. So 2,2-dimethylpropane and N-pentane and 2-methylbutane, they are what? They are isomers. Why are they isomers? Because they have the same molecular formula but different structure. I hope that is clear. So that is how to know the isomers. If somebody may want to ask me, is there a formula that we use to know the number of isomers? There is no constant formula. If anybody has shown you, they're just playing. because it keeps changing. Like this is a very big calculation. It doesn't just follow that in how many ways can we arrange carbon and hydrogen. It doesn't follow all those things. You can use permutation and combination formula to do. All right. So it's because once you can join, look at what I'm saying, that despite the fact that I can put carbon here, I put another one here, it's still not the same compound. So it's very difficult for us to have a computer kind of stuff that can work out this. So most formula that we use, I've tried to derive some myself to help students to know that, oh, if you use this formula, you know the number of isomers, so you can think, all right, how to do it. But those formulas are not consistent. All right, once you keep increasing, it keeps changing. And then so all you need to do is just, like, first of all, learn to write this very well. All right, write it very well, write the structure, and think about how you can build up structure. The more you think, the better you become. Like, oh, let me see. Now if I ask you, is there another way of arranging this guy to make sure that it is another isomer? So maybe there is none, maybe there is. Okay, let's even try whether we'll have something like this guy. When you have 3, then you have 2C. Let's just look at it. I'm just showing you. Okay, as long as open chain like this, there is none. So this is H. That is how your brain should be working. Like, I want to see how we can do that. Can you see that it's not complete? 1, 2, 3, 4, 5. But the hydrogen will never complete because of this ring. All right, remember this part. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8. So you can see that hydrogen is not complete. 1, 2, 3, 4, 5, 6, 7, 8, 9. So we are going to C5H12. All right. So that is the one. If you want to make it the one of cyclobutane, this is 1, 2, 3, 4, 5, 6. Then you now put the next carbon here. This one will be CH3. So you can see that. So that is just the isomers. Okay. These are isomers that we have 3. We can only have 3 isomers for C5H12. All right. The first one is N-pentane. The second one is 2-methylbutane, while the third one is 2,2-dimethylpropane. All right. So let's increase it further and now see if we're giving 6,6H14. You know the reason why I'm doing this. I'm not going to explore this. 2 times 2, 12 plus 2. So this is an alkane. If they tell you why is 6,6H14, why is it an alkane? All right, you will say because it conforms with the general formula CnH2n plus 2. That's all. C6H2 times 2, 12 plus 2. 6H14. So it is an alkane. So let's try to work out all the possible isomers for 6,6H what? H14. All right, but I'm not going to finish it. It's not like that there are many like that we can't finish. But I want to give that room for you to keep thinking and keep working out. So, and I want you to drop it in the comment section. All right, the other one you got. I'm just going to write 3. There are so many of it. They are not 3, they are not 4, they are not 5. All right, so we keep working to get everything. All right. So the first one we have to be that 6. All right, 1, 2, 3, 4, 5, 6. But that's the normal one. All right. So the hydrogen will just fit. Once I complete this one, I know that this one has only 1 bond. So it's going to have 3. Some will have 2. So 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So it clicks. It's not something that you, let me put hydrogen. How many? Don't bother yourself. Just make hydrogen to have, carbon to have 4 bonds around it with hydrogen. Then you're good to go. All right. So this is the first one. This is the first isomer of that molecular formula 6,6H14. All right. So what is this called? This is just hexane, normal hexane. We call it N-hexane. All right. So I hope that is clear. Call it N-hexane, and that is beautiful. All right. So if you look at the second one, okay. So quickly pause the video and let's go. The second one, what can it be? So what do you think you will do with the second one? I really want you to go ahead and do that. Okay. The second one will be what? That second one will be what? Let's work it out. Second one will be what? All right. The second one will be when you reduce the 6, 6 to C5. 1, 2, 3, 4, 5. Okay. But remember, you're not going to place it at the extreme. Okay, carbon atoms. No, don't try that. If you put the one carbon here, it's still going to be like this because I can straighten it. So let's place it here. All right. So that is it. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Can you see? It will just be complete. Just show you that don't bother about wasting your time counting. Make sure all the carbon atoms, they have 4 bonds around them. All right. Once that is ensured, then the number of hydrogen will be complete. All right. So this is very simple. We have the longest chain now to be what? To be 5. So write it pentane. What is the name of an alkane with 5 carbon atoms? That is pentane. 1, 2, 3, 4, 5. Remember, at position 2, we have methyl group. So that is methyl. Methyl will be here. But that methyl is attached to carbon number 2. That's what we are doing. Very simple, very easy. This is 2-methyl pentane. All right. The third one, let me put it here. All right, the third one. All right. Look at the third one. Should I reduce it further? No, because I can move this guy to this place. 1, 2, 3, 4, 5. Can you see that? If I move this C to this place, is it different from this? The answer is yes. Okay, if I name from here, it's going to be 1, 2, 3. If I name from 1 to 3, so that shows that anywhere you move, you get the same compound. This compound is different from this and this. So what you do is just pick there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. I think don't decide. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Alright, so that is it. This is still a methyl group. But now that methyl group, irrespective of the side you're coming from, is at position number 3. So that is 3-methyl. What? 1, 2, 3, 4, 5. That is still pentane. So this guy has C5H12. This guy, 2-methyl pentane, has C5H12. This N-hexane also has C5H12. And they have different structures. Of course, that is why they're having different names. So N-hexane, 2-methyl pentane, and 3-methyl pentane. They are all isomers. Alright, are there more isomers for this 6H14? Yes, I can see so many. Alright, we're still on 5. We have not reduced the bond to 4. We have not reduced it to 3. If it is possible. Do you understand? So, and we still have that. So let's see how you're going to put the structures and the names in the comment section. Let me just put 4, 5. Okay. So let me put 6 actually. So can you keep working out the isomers for this particular molecular formula? All right. So put this in the comment section. Any isomer you get one that is different from all these. Put it as number 4. You get another one, put it number 5. Another one. So just keep working out the isomers. Remember, they must have the same molecular formula and different structures, which is going to be different names. Don't repeat compounds. Students make a lot of mistakes from that because they don't know which compound is which. I've shown you how to know that, oh, this particular compound is still the same compound as this, if you don't know. So this is what we call isomerism, and I believe that is very simple. All right, so that is where we're going to be ending the name, which is nomenclature, and we have ended the isomerism as well. All right, so we're not going to pick methane as a representative member, and we're going to do that very fast so that this video will not be unnecessarily lengthy. All right, let's quickly pick methane, and so we'll talk about the reactions of alkane. Okay, so methane is a representative member, or I want to pick methane because we're going to pick them one after the other. All right, as a representative member of alkane homologous series. I'll just talk about its reaction and some of the other ones that are similar to that. All right, methane. Sometimes you find it in the decay of vegetations, all those plant materials. So we call it marsh gas. All right, because of that, called it marsh gas. All right, and it's also the major component of natural gas. All right, some of you don't know that natural gas comes with petroleum. All right, I read something funny about this country the last time. Someone said a writer is even outside the country. I read it about maybe like 15 years ago, saying that Nigeria has more of natural gas than petroleum. All right, if you know that statement I just made, you know what it means. It means Nigeria is very rich. We have more of natural gas than petroleum. And the natural gas we have can light up the African continent for 1,000 years. All right, a white man actually wrote that about Nigeria. So most of the time, we are wasting this gas, call it gas flaring. All right, natural gas sits on top of petroleum. When you put your, let's say, drilling pipe, what comes out first is natural gas before you now get the crude. Okay, so you can convert it to most of the gases that you use for cooking. Just like, you know, if I talk about your cooking gas in your kitchen, some of you have not even talked about it, like, oh, is it cooking gas, is it hydrogen gas, is it oxygen gas, is it nitrogen gas? It's actually hydrocarbon. All right, those gases are hydrocarbons, alkanes particularly. Now ask me, is it methane? Yeah, we have a mixture of methane is there, ethane is there. I've seen another gas, some people say C3C4, that is propane butane mixture. It's actually nice. Some will say ethane, methane, ethane, butane together. All right, it's not a single gas that you're filling your gas cylinder in your kitchen. So it's a combination of the gases, usually C1 to C4. All right, okay, there are gases that we use. All right, so it's called marsh gas because I say it's evolving from the vegetation, decaying vegetation, and also is the major component of a natural gas, and I just explained that now. All right, so that is methane. All right, and it's the first member of alkane homologous series. First member with the formula CH4. All right, look at that, CH4. All right, look at that. In terms of structure, don't let me say, look at the way it looks flat. It's not planar. What I mean is that it's not flat like that on the board. All right, some bonds are actually going away from me, some coming away from me. So that's why sometimes the bond going away from you will fade it. You do like this. The one that is coming towards you, seeing the more clear, is a thick wedge. All right, the one that is on the plane will look like that. So let's look at this like we have 4 bonds. All right, just look at it. You have a rope. You have something like, we nail this rope, 4 ropes to this place, and these are the 4 people that don't like each other, and they want to stay far apart, away from one another. Some of you will think like this is actually the best way they can stay, when they will have 90 degrees to each other. I've entered bonding now, but okay, let me just continue because it's interesting, and we're talking about methane still, right? So look at this, hydrogen, 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 hydrogen. They want to stay away from each other as possible, just like I'm standing like this and I'm holding 4 ropes, equal lengths. All right, and those guys around me, they want to stay away from each other. If this move close, you push, get away from me, because they don't like each other. Why? Because this bond, electrons are used in making the bond, and electrons are negatively charged. So there's a repulsion between this. So I'm using what we call valence shell electron pair repulsion theory. All right, that's what I'm using. So the bond here, they keep repelling each other. They want to stay as much as possible away from one another. So in what possible ways do you think they can stay? All right, if I have 2 persons, let's say someone is there. All right, one person stay here, another person stay here. Can you see? So this is not the best they can stay from each other. Do you know? Because this angle is still small. They can still say, please stay away from me. The best way is one to be here, another one to be here. Can you see? That's 180 degrees. So that's what we are talking about. How best can these two people stay away from one another? Is when the bond angle between them becomes 180, all right? So that is what we are saying. Now look at this one. How best can you think they can stay? Some of you would think it's this cross. When this one. That is when the stuff is planar. It's not planar, okay? So take note of that. It's not planar. When it is planar, all right, you can say, this one wants to stay away like that. That is not the highest. Do you know this is 90? Hydrogen find a way to stay away from one another at 109.5 degrees. Can you see that? Instead of it to be 90. So that's how you understand that. In fact, there is a better way of staying for 4 people to stay away from each other, and then the bond angle will still be more than 90. This is how it is. Picture it as something moving, like this one is not just standing. It's moving away from this one, is coming towards me, and this one is on planar one. So what I'm trying to say is just like 109.5 degrees is the bond angle of every HCN. See at the bottom. So this bond angle. So because it's not planar, it just like it looks like. I'll actually maybe I'll put it on the screen for you to see the structure of methane. So hydrogen can stay away from each other with this bond angle. It's so funny, all right, and so interesting to show that it's not 90 degrees that is the maximum angle that can be between them, and that is why this is a perfect tetrahedra. All right. Each of these hydrogens is pointing to the corners of the tetrahedron. All right. So 109 degrees is the angle. HCH. It's not 90. All right, because it looks like this. Look at my finger. So the carbon is like this, then they are pointing away from one another in a very funny way. That is not planar 90. If they planar like this, place it on the board, then you find out that 90 degrees is where they, but it forms a particular bond angle. Call it a tetrahedron. That is 109.5 degrees. So that is methane structure. I just use valence shell electron pair repulsion. All right, maybe when we have some simulation, we'll be able to see it clearly. But I'm going to put a picture of how it looks exactly, so you know that it's not planar. I'll be able to see the bond angle that I'm talking about, because each bond tries to push the other bond next to it the same way. So they try to stay as far apart as possible, and they're able to find a very comfortable configuration, the stable structure, and that forms that bond angle. All right, so that is methane. So let's now talk about number 1, preparation, laboratory preparation. Okay, laboratory preparation of methane. All right, so remember, methane is a representative member. We say all members, we use homologous series. In the part 1, we said that every member share a general formula. That shows that alkanes generally, they follow CnH2 plus 2. Alkane also, methane follow because that's 1 carbon. So C1H21 plus 2, that is CH4. All right. So ethane will follow. So laboratory preparation also, whatever you have used to prepare methane, you can use it to prepare ethane too. All right. In that first video, I was talking about if you're preparing rice for 1 person, you're going to prepare it the similar way, not the same. Similar way for 2 people, for 10 people. Why is it not the same? Because same is a very strict scientific term. We use the same thing, so exactly the same quantity of heat energy, the same size of pot, the same quantity of water, the same. All right, but similar means that the same method you prepare is the similar method. You do the same thing, but you may increase the quantity. All right, lab preparation of methane. When you want to prepare methane or any other alkanes, okay, but we're starting with methane, so you see how it works. Okay, we grind a mixture of sodium methanoate. We're not wasting time. Sodium methanoate is this. I'll get to other organic compound. You know that this is sodium ethanoic acid. So sodium methanoate with NaOH. But look at this. Sodium hydroxide is very deliquescent. Remember, it's the gas you want to produce from here. So getting water getting water around here will make the stuff messy. So sodium hydroxide now wants to invite water, all right, because this is the reaction that will cause the stuff to go on, all right. So because it's deliquescent, what does it mean? It invites water. A deliquescent substance is a substance that absorbs so much water from the atmosphere when exposed, and if they are solid, they dissolve in the water to show the quantity of the water they absorb. So in order for you not to, we now mix it with calcium hydroxide, all right. This is caustic soda. We call it caustic soda, all right. We call this one quick lime, all right. So when you mix the two together, this gas still retains its properties, but in a way it's going to form, if you have ever seen before, it's form a solid that is no longer deliquescent. That solid that will form from these two will no longer be deliquescent. Nothing has happened to this NaOH, nothing has happened to this NaOH, but their mixture, their association forms a solid that if you drop it on the table, it's not going to absorb water. So that is what we call soda lime. Can you see? So we call this mixture soda lime. Don't forget that. We call it soda lime because it's from caustic soda and quick lime. So it's called soda lime. So this soda lime is preferred in this laboratory preparation because we don't want to imbibe water. It is not deliquescent and it does not attack glass. As you know that we're going to put this guy here now. The mixture of this sodium ethanoate and soda lime will be here. We'll subject it to it. Then we'll take the delivery tube. These are glasswares. Then we'll pass it through the trough that has water. You know, all these gas collections. I'm going to put the main diagram there so you can see. So what I'm saying, just like the disadvantages of using only sodium hydroxide. Only sodium, I've used sodium. Number one, sodium hydroxide alone is deliquescent, okay, deliquescent, and it also attacks glass, all right. If you have done titration, if you are doing titration very well, you will see that sometimes when you use sodium hydroxide, by chance, maybe you pour it through a base, through the burette, and you didn't wash it out completely, you just forgot, oh, maybe by mistake you want to put acid there, because most of the time at some level you just feel that acid is the only one that will be in the burette. No, anything can be there actually. What is important is just like if you put base there and put acid there, they will react. Now the contact is what causes the reaction, not where you put them, all right. But we don't always want to put it at your level because it will cause the burette to knock, because it reacts with glass and you'll be able to open the tap again and it gets stuck. So sodium hydroxide is deliquescent. It's going to invite water. We don't want water here, all right, and then it also attacks glass. But soda lime is preferred because it is not deliquescent and does not attack glass, all right. This is preferred because it's what? It is not deliquescent and it does not attack glass, all right. That is why soda lime is preferred. It does not attack glass, it is not deliquescent, and that's why it is being used. So CaO does not do anything. NaOH still retains its chemical nature. CaO just improves the property, all right, so that it does not behave like this. We don't want it to behave this way, all right, but we still want to carry out reaction. So that's why it's used. So in the chemical reaction, you don't put CaO, all right, because it's called soda that will stick the react, okay. But this is now soda lime. Sodium hydroxide coming from soda lime. That is the CaO select with the concentrated solution of sodium hydroxide. Now, what will be this reaction once you subject them to heat? All right, you will see that. Look at what I want to do. Look at this. What is this? I've seen that one pattern there. That is Na2CO3. Na2CO3. Look at it very well. That's sodium carbonate. Plus CH3 and H remaining. That is CH4. So that is methane that we're looking for. Alright. So it's very simple. That means that if you want to produce another higher members of alkane, you don't have to use sodium ethanoate. This is sodium ethanoate. Okay. If I use sodium propanoate, CH3, CH2, COONA. This is sodium propanoate. Can you see? Sodium propanoic acid. It's just like CH3, CH2, can you see? COONA. So that is sodium propanoate. Can you see that? So this is propanoate. You react it with the soda lime again. Can you see? So look at this fragment that I mapped out from that place. It's still there. So this is the Na what? Can you see? That is the Na2CO3. See here. Plus, what do you have? CH3CH2 plus H. That is C2H6. So C2H6 is ethane. That's why one of the properties of homologous series says that they have similar method of preparation. Can you see? This is not same method. Because if it is same, you are going to use sodium ethanoate here too. But the similar method, because we just increase the carbon chain of this particular salt. Alright, so this is propanoate, okay? Sodium propanoate, sodium ethanoate. So sodium ethanoate produce methane. Sodium propanoate produce ethane. So butanoate produce the other one. So you can continue to go on and on. If I want to produce another one, alkane, I will just increase this carbon chain. Let me do that one last so that you can see that. So this is sodium propanoate. The next one will be sodium butanate. Let's say sodium butanate. It's going to have CH3. I hope you have seen that. Let me lower it a bit. CH3, CH2, CH2, COONA. This is sodium butanate because sodium 1, 2, 3, 4, carbon is 4. So we have sodium butanate plus what? NaOH. So work out this guy. Can you see? That is the NaCO3, Na2CO3. Okay. Plus 1, 2, 3. This is C4. Can you see? Is it the C3? Look at it. C. So in other words, I can say CH3, CH2, CH what? CH3. This is C3 what? H what? H8, which is propane. Okay, so that is the way we continue to produce alkane using the same similar method. So methane is produced by heating what? The Gram mixture of the anhydrous sodium ethanoate with soda lime. Alright, soda lime is just like quick lime slaked with the concentrate of sodium hydroxide to improve its property. The property is like, this is the liquid, this is attached glass. But when you grind it with CaO, which is quick lime, it gives that property that we need. The property that does not is not liquescent again and it's not going to attack glass. Okay, so that is by that. Okay, so that is the laboratory preparation of that. So let's now talk about the reactions of methane or alkanes, and we're going to talk about just 3 reactions, and that's where we're going to end that. Reaction, chemical reaction of what? Alkanes. Okay. All right, so we have that reactions. We have that preparation, and I hope that is clear. All right, the first reaction is combustion. It's very important. Combustion, okay, of alkanes. Okay, when you carry out combustion of alkanes, this is the reason why you can use alkanes in your kitchen, all right, because they can burn, all right, and they have the low content of carbon. You're going to know that when we start relating the combustion of alkanes with that of alkanes and alkynes. So combustion of alkanes, when you carry out combustion of alkanes. What are the products that you will get? Alkanes has C and it has hydrogen. So once you carry out combustion, presence of oxygen, carbon will pick up oxygen to form CO2. Hydrogen will pick up oxygen to form what? Water. But carbon and hydrogen, which one do you think loves oxygen more? Alright, this guy has the serious affinity for oxygen. So water is formed, then carbon dioxide is formed. That is when oxygen is in excess. Alright, if there is limited supply of oxygen, instead of water will be formed because it's the first thing that will pick up the oxygen. It has more love for oxygen than carbon. Alright, so but this one, the oxygen will not be enough. So we can form C, we can even form CO and C. If this is a limited supply of oxygen. Limited means that there is no supply of oxygen. That means oxygen is limited. It's no longer, it's not that much. We have just little supply of oxygen, so it's limited in supply. Okay, so let's quickly. So when we talk about combustion of alkanes, we simply mean excess oxygen. If it is not in excess, they will tell you that it's limited. All right, so always know that CO2 and CH2 will be formed. All right, so let's say methane like this will react with O2 to form CO2 and H2O. All right, so that is it. All right, so we'll just balance it. Okay, we'll balance it. And how do you balance that? Because C is 4 here, so you put 2 here. All right, so then oxygen is 2 and 2, making 4. You put 2 here. So this is balanced. All right. So we have formula for doing this combustion of alkanes. All right, let me just give you CXHY. That means X is C is 1 here, H is 4, plus what? X plus Y over 4 O2 will give you XCO2 plus Y over 2 H2O. All right. So this is the formula. All right. But the point is, I don't like this formula. All right. I just have to give you. All right. I don't like it in the sense that what about if you forget? Some of you will now want to write it somewhere and say because it works wonder. Let's look at CH4. CH4 meaning like X is 1, Y is 4. So plus X is 1 plus Y is 4. Look at this now. Y is 4 for CH4. 4 over 4. You put O2 there. We give you XCO2. X is 1 CO2 plus Y over 2. Y is 4. 4 over 2 H2O. So what is that? CH4 plus, cut it, that is 2 O2. We give you 1 CO2 plus 2 H2O. You can see that it gives us the same thing. All right. So, but there is no point cramming this formula. I wanted to write it. I almost forgot, but because I've been using it for years, so I can't forget. All right. So, but what about if I forget? During exam, I'm writing the exam, I forget. So just understand that whenever you are giving alkane, hydrocarbon, CO2 and H2O will be formed. Then balance the equation. If you don't know how to balance the equation, then we have begin to say, oh, this is difficult. So how do you go about that? Okay. So the way we balance the equation is very, very simple. It depends on anything they give you. It's not your business. All right, it's not your business. You always get it. If they give you C2, what is the next one? C2H6. This is what you want to carry out combustion. Plus O2. All you need to do is just say CO2 plus H2O. Okay, so that is what will be formed. Then you now begin to say, oh, what will I do? Look at this. C2 is here, put 2 here. All right. H6 is here, put 3 here to make 6. Now count oxygen. That is 7. This is 4. That is 7. All right. Put 7 here. But divided by 2. You know the reason. All right. Why did I do that? let me show you what I did from the beginning so that you won't say, oh, this is difficult. So, all right, it's not difficult. Once you write ethane plus O2, it forms CO2 plus H2O. Because C2 is here, put 2 here. I hope you have seen that. All right, because H6 is there, put 3 here to make hydrogen to be 6 too. Now, 2 times 2, that is 4. 3 oxygen, so that makes it 7. But you can see that 7 oxygen is now 14 here. So when you divide it by 2, that is it. So if you now multiply everything by 2, so you have 2C2H6 here plus 7O2. Multiply everything by 2. So the 2 will cancel that. So this 2 will come here. 2 will cancel that. Then we have 4CO2 plus 6H2O. So that is it. If it is 1 mole of ethane, this is it. So 2. Can you see? If you use this formula also, work out this formula, you will do it. So it's very, very simple. Very, very simple. Let's work out if it were to be combustion of the third one, which is this is ethane. Let's say propane. Propane is C3H times 2 plus C3H8. Alright? If you use the formula, it's like it has come out already. That's your problem. Okay? Look at this. 3 plus 8 over 4. That will give you 3 plus, okay, so, and then you think, oh, that's good. Alright, let's do this. Plus O2 will give us CO2 plus H2O. It's very simple. So just understand that excess, you're going to do that. Alright, for the other one too, if it is limited, just write it in CO. Alright, and then you balance your equation. So balanced equation is just what your problem is. Alright, if they say is limited supply of oxygen, instead of you to put CO2, put CO here and balance it. Alright, balance the equation. Okay, so let's see what we have to do now. So because 3 is there, put 3 here. Because 4 is there, put 4 here. So 3 times this, that is 6. 6 plus 4, that is 10. That makes it 5. Alright, then everything is balanced. Alright, so that is the way it is, isn't it? That is it. If you had used the formula will give you the same thing. Alright, look at that. This is your x, this is y. So let's say x plus y over 4, that is 3 plus 8 over 4, O2, x CO2, so 3 CO2, plus y over 2, 8 over 2 H2O. So it gives us the same thing, C3H8 plus, that is 5 O2, will give you 3 CO2 plus 4 H2O. Alright, so but when you know how to balance the chemical equation, then it becomes very easy for you. Alright, I hope we have seen this. This is very simple. So this is the combustion of alkanes. When they burn with a very clear flame, it's not sooty because the proportion of carbon to hydrogen is much. Alright, proportion of carbon to hydrogen is low. So unlike alkenes and alkynes, which we're going to compare them when we get to alkenes. Alright, so that's the reason why you are using this guy. It gives very exothermic, very hot flame. Okay, and the flames are clean. Alright, so they form CO2 and H2O. Alright, so this is the combustion of alkane. That's the first one. The second one is called free radical substitution. So alkanes undergo some substitution reaction, and we have to quickly talk about this. Okay, let's say methane. When methane reacts with chlorine, when methane, that is, let me call it substitution reaction. Substitution reaction. It's called free radical substitution. Alright? Because let's say methane reacts with chlorine in the presence of UV light. Let's say like that. Methane reacts with chlorine to form a mixture of products in the what? In the presence of UV light, which acts as a catalyst. All right, so this reaction is also called free radical substitution, because the first thing that happens is that Cl2 will be UV light will act on it to now form those radicals, which are very reactive. These are the reactive species that will attack chlorine, that will attack the methane, and they keep substituting for hydrogen there. All right, but I'll make the reaction in steps so that it's going to be very easy for you. All right, so we have CH4 react with chlorine, the presence of UV light. All right, CH4. So what will happen is, after this chlorine split into this, all right, it's going to attack this guy. All right, it's going to attack this this one. So let's say it forms CH3Cl. All right, so the other hydrogen that is knocked off will now combine with the second one to form HCl. All right, so this is what we call Cl. That is the first step. Look at that. It's chloromethane. Chloromethane plus HCl is formed. All right, so the reaction will continue. Chloromethane will react with chlorine. Chlorine again. All right, this UV light will still split chlorine into the radical. This one will attack another hydrogen. Hydrogen will be knocked off. So we have CH2Cl2 plus HCl. The H that comes out will combine with the second one. All right, so we form HCl. That was the excess chlorine. So this is dichloromethane. Okay, dichloromethane. This chloromethane looks like this. 1Cl, then H will now be like this. It looks like methane, but chlorine has to call it chloromethane. The second one is dichloromethane. Okay, so dichloromethane will be the one to start again. Can you see that? CH2Cl2 plus Cl2 again. I don't have to do this again. 1Cl will knock off that. We now form CHCl3 plus HCl, right? This is called trichloromethane. Okay, it's what we call chloroform. There was a year I was working with white rats. Now some of you will be wondering, like, why white rats? Okay, when you're carrying an experiment, it's better to use those white rats, not all those black demonic rats. Black rats, white rats, they become your friends with time. You feed them, all right. I was in there from an experiment. I want to feed them some certain things. Then later I would check their heart, check their liver, and see the effect of that feed on them. All right, whether it has affected their blood, or it has affected the organs and stuff like that. So if you keep black rats in a cage and you want to be feeding them, the next time you come, they will tear the cage and they have gone. So, but a white rat, have you seen them? Call them albino rats. So they are just obedient. They'll be looking like this, waiting for you for their first food, what is it called, breakfast, lunch, and all that. So very, very beautiful to work with. So there was a time now at the end of the experiment, I need to slice them open. All right, just to collect the organs, collect the blood for all those histology and hematology tests. All right, so you need chloroform to knock them out. That is trichloromethane. All right, you just soak it inside cotton wool, and once they come and see they want to eat, maybe they perceive it, they will just fall off. So that is chloroform. Chloroform was used before too, you know, in hospitals as anesthetic agents. When you want to operate on patients, they just give it to you and then you sleep off and then. But there are better ones. Like the first compound we named, that is halotane, is far better now. All right. So imagine they give you chloroform and you don't wake up again after the experiment, after the operation. So there are a lot of compounds that are better than chloroform now. So that's why we have thrown chloroform away. But when it comes to working with animals in universities, we still use chloroform to knock them out. Okay, knock them out so you can operate on them. All right. So that is the third stuff being here. But we still have hydrogen in chloroform. So chloroform will now serve again as the fourth reactant here. All right, CHCl3 plus Cl2 will now give us what is it called? CCl4 plus HCl. All right, so this is tetrachloromethane. All right, tetrachloromethane is CCl4. All right, there's no hydrogen there, but it's still named after methane, tetrachloromethane. So when methane reacts with chlorine to form, it forms a mixture of products like this. So that shows that we form chloromethane, dichloromethane, trichloromethane, and tetrachloromethane. So trichloromethane and tetrachloromethane, this one is used as an anesthetic agent. All right, you can see the rest are majorly solvent. Dichloromethane, DCl. All right, tetrachloromethane, we call it carbon tet. They are used basically as solvent. All right, but you can see the reaction. So that is it. If you had used ethane, we continue to substitute for hydrogen. As long as we have excess chlorine under UV light, chlorine will substitute for them till we get to hexachloroethane, because the first one will be chloroethane, dichloroethane, trichloroethane, tetrachloroethane. So we have this mixture of products. And you can see that from here we have 4 HCl. All right, 4 HCl products. All right, one here, one here, one here, one here. Then we have chloromethane, dichloromethane. So that is the second reaction of alkanes. Another reaction that is just like kind of reaction of alkane, which is the last one, is this. When you have alkane decomposing, that is long alkane decomposing. All right, long alkane decomposing. Okay, so that is number 3, which is cracking. All right, so we call it cracking, just like the name, crack. All right, we crack unnecessarily long chain alkanes. Alkanes are the shorter forms are very useful. All right, the shorter alkanes, they are the ones that we use for as solvents and stuff like that. All right, but when alkanes are unnecessarily long, all right, it's less useful and it's not in demand. All right, so people don't use it for anything. So that's why industries, after petroleum and all that, after all the processes, and you get unnecessarily long alkanes, we break them into the shorter ones that are very useful. Okay, let me tell you what I mean. If you have C10, H what? H22. So you can crack it into different substances. Okay, let's say I want to crack it into, I want to put butane, because I want to use that, I want to sell it as part of the, because I've told you like we have C3C4 mixture. Butane is part of the cooking gas that people use every day. So C4H10 is butane. Okay, what to be left is what? To be 6,6 what? 6,6. After we have taken C4H10, so it will be what? 6 is H what? H12. All right, 6 is H12. Can you see that? 6 is H12. So let's say that some people are saying that, oh, we use ethene to form polythene in the production of plastics. So let's form ethene from it. Okay, so I now form butane for cooking gas. Then another demand, C2H4. This is butane, which is part of cooking gas. This is ethene, which is what? Which is for making plastics, okay, PVC and stuff like that. Now, we have C4, we have C2. What remains is what? Remains C4 too, all right? Can you see that? So C4, 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 that is C10, all right? C4, C4, C2, that is C10. 10 plus 4, that is 14. How many? 22 minus 14. Okay, that is 8. So, can you see? So we have butene or butane. This one can be very useful too in industry. So you can see that I've cracked long chain hydrocarbon into shorter ones that are very useful. So these shorter ones are more useful than the long ones. So that's what we call cracking. So there are different ways you can crack different substances, and they form different lower chain or alkane. When you crack, basically when you form alkane, you form alkane. We can even form hydrogen. All right, remember that if you crack this guy, when you remove hydrogen from alkane, you get alkane. So we can crack alkane. We crack alkane, you get alkane plus alkane. Alkane plus alkane. Okay, just like these two can form one alkane. All right, we can crack alkane. We form alkene plus hydrogen. All right. So anyhow you crack it, you just see that lower alkanes are possible that are very, very useful, right? So those are the three reactions of alkane homologous. So remember where we started from part 1, we introduced alkanes, and at the same time we told you that alkanes are the most important organic compound in the sense that every other organic compound such as alkene, alkynes, alkanols, alkanones, esters, all of them, they depend on these guys, okay, because they are named after them. Their roots, they come from here. So if you don't understand alkene very well, even naming those compounds will be very difficult, and their reaction will not be able to understand that. All right, so we now move to naming, which is called nomenclature, and we're able to do justice to rules. We didn't state the rules, so to say, so that the class won't be boring, and at the same time you won't get bored, because if I state all the rules, like 10 rules, 8 rules, and then you'll be like, we have to put it. But once you apply, we just applied it, and you find out that you're able to put things together. So please don't forget that the first video, which is part 1 of alkanes, very important. Then when we move to the second part, when we continue with the naming, then we extended it to isomerism, which is the essence of 2 or more compounds with the same molecular formula or different structural formula. Then we talked about the representative member, which is methane. And how do we prepare methane? We also try to look at how we can prepare any other bigger alkanes using the similar method. All right, then we're able to do that. Then we pick alkane, methane as a representative member, talking about the reactions. The first one was combustion. I gave you a formula, and I told you that it's very important for you to learn that when you want to write the formula, all right, you can forget the formula, all right, under the exam conditions. It's better for you to just know that if they talk about alkane, methane bonds in excess oxygen, just write oxygen, you know that CO2 plus H2. Balance it. They say limited supply of oxygen, H4 plus O2, make it CO and balance it. It's very simple. Once you can count atoms and put numbers here, then you're good to go. So that is just the way it is. Then we'll move to the substitution reaction, which we also call free radical substitution, because what is actually happening is the splitting of these chlorine molecules by UV light into this reactive species, which keeps attacking the molecules of methane to produce this substrate product. They will move to cracking, which is very important. That the long, unnecessarily long alkane is it's not that useful, all right, or less importance in industries, and then but these lower ones are in high demand, so we can break down the long chains into smaller chains so that we can use it. For example, look at butane can be part of your cooking gas. Ethane can be your, what is it called? Can be used for polymers, including butane. All right. So that is just this. And this comes to the end of alkanes. And I want to believe that if you're writing WAEC, you're writing JAMB, this is very useful. Part 1 and part 2, all you need to know about alkanes. All right. So please don't forget to subscribe to the channel. It doesn't cost you anything. It just means that anytime a new video is dropped, you'll be one of the first set of people to see it. All right, just make sure you subscribe and make sure you share to friends. Comment if there is any topic that bothers you, all right, as far as chemistry is concerned. Please put it in the comment section. You may be lucky, I'll pick it. It will be the next video you will see in my channel. So please till the next video, see you. Bye for now.